Okay, so we're talking about um, splitting fields and algebraic closures. So first I'm going to review what we did on Wednesday, and then we'll start talking about algebraic closures. All right, so on Wednesday we talked about... Okay, so hold on, there are new people. All right. Yeah, so I was saying, on Wednesday we were talking about splitting fields. So what is a splitting field? So you have an extension of fields. So K is an extension of F. This means like F is a subfield of K. And this extension is called the splitting field for the polynomial f of x. So f of x has coefficients in the ground field f. So this extension is called the splitting field for this polynomial f of x if the polynomial f of x splits completely into linear factors in k of x. So when you extend your realm of coefficients from the field of f to the field of k, right, you get your polynomial splits, right? So if it does factor completely into linear factors, we say the polynomial splits completely. And furthermore, for it to be a splitting field, we require that the polynomial f of x does not split completely over any proper subfield of k containing f. So k is the smallest field where your polynomial f of x splits completely. In other words, like all of the roots of your polynomial are in this extension k. So here are some examples. Right. So here are some examples. So we start with the base field. This is the field f, right? So the ground field or base field is going to be q in all of these cases. And then we have to consider a polynomial. So the first, let's consider the polynomial x squared minus 2. So this is an irreducible polynomial over q, but if you move up to the splitting field q adjoin square root of 2, now you have a new element called the square root of 2, and so this polynomial splits. It's actually splits in this new field. It's going to split as x minus square root of 2 and x plus square root of 2. Right, so it splits into a product of linear factors. In other words, like this polynomial has all of its roots in this splitting field. So that's why this is called the splitting field of this polynomial over this base field, because all of the roots are in here, and this is the smallest field that where this polynomial splits. All right, second example is q is the base field, and then our polynomial is a product of two quadratics, x squared minus 2, x squared minus 3. The splitting field is q adjoin square root of 2 adjoin square root of 3. All right, again, you can, in this new splitting field, you can write this as x minus square root of 2, x plus square root of 2, x minus square root of 3, x plus square root of 3, and all of those terms are linear factors. Okay, so yeah, splitting field means your polynomial has all of its roots in this field. A third example is x cubed minus 2. The splitting field is q adjoin square root of 2 adjoin the third root of unity. So the third root of unity omega is a number such that omega cubed equals 1, right? So in the complex numbers, this is like 1 minus square root of I forgot, whatever. So omega is just e to the 2 pi I over 3. Right, so when you square this, right, you get 1. Okay, so yeah, why do you need to have omega as well as square root of 2 to make this the splitting field? Because this polynomial actually has 3 distinct roots. It has cube root of 2, it has omega cube root of 2, and it has omega squared cube root of 2. And if you cube all of those things, you get 2, right? So the 3 distinct roots of this polynomial are in this field. Okay. And the fourth example is the base field is q, and the polynomial is x to the fourth plus 4. here the splitting field is Q adjoint I, because you can write this as x minus what? Well, you can write this as, okay, someone's here. Alright, so we were just talking about splitting fields and some examples of splitting fields. So the splitting field of x to the fourth plus 4 is Q adjoint I, because what are the roots of this polynomial, x to the fourth plus 4? Well, you have, okay, so first you could write this as x squared minus 2i, x squared plus 2i, right? And then each of those, you could write it as, oh, alright. So actually the roots of this polynomial are plus minus 1 plus minus I, right? If you take this to the fourth, you should get 4. Oh, wait, you should get minus 4. Yeah. And then, and then plus minus 1 plus minus I, these all live in that field, and the smallest field containing all of these roots is Q adjoint I. So this example shows you that the degree of the splitting field can actually be smaller than the degree of the polynomial, because this is not an irreducible polynomial. Let's see. Yeah, so this is not an irreducible polynomial, so the degree of the extension is not necessarily the degree of the polynomial. So when you split this up, you get x squared plus 2x plus 2 times x squared minus 2x plus 2. And then each of these split like x minus 1 plus I, x plus 1 plus I, x minus 1 minus I, and x minus 1 plus I. Yeah. Okay. So yeah, so the roots of this polynomial are at, like, they're distinct roots, but they all give you the same extension, right? Q adjoint I, right? Whereas the roots of these two separate polynomials would give you different algebraic elements. Right. Okay, so those are splitting fields. Right. No. And then we proved the existence of splitting fields. We proved the existence of splitting fields via induction on the degree of the degree of the polynomial. So we did this on Wednesday. We also have this proposition: a splitting field of degree n over f is of degree at most n factorial over f. Right. Okay. And finally, we had two examples. We had the splitting field of x to the n minus 1, which is called the nth cyclotomic field, and we had the splitting field of x to the p minus 2, which is this splitting field. You would join the pth root of 2. This is a real positive root, and you would join the pth root of unity. Okay. So this was all stuff from Wednesday. Are there any questions about this? is the claim, yes, I am recording this, is the claim that the polynomial of the splitting field of degree at most n factorial, of course a field of degree n has at most, is of at most n factorial. Wait, what is this question? Is the claim that the polynomial of the splitting field So this proposition states a splitting field of degree n over of a degree n. Yeah. Okay, so I wrote it wrong. So the proposition should read a splitting field of a degree n polynomial over f. Okay, thank you for catching that. So a splitting field of a degree n polynomial over f is of degree at most n factorial. Right? Good. Okay. Now let's continue. Alright. So now what are we talking about today? So we're gonna talk about, what is it? We're gonna talk about algebraic closures. Right, algebraic closures. So the first thing we need is this theorem, which is a generalization, okay. Alright, let me just read what it says. So let phi be an isomorphism between two fields. So these fields are basically the same because there's an isomorphism between them. So f and f prime. There's an isomorphism of fields. Let f of x be a polynomial with coefficients in the first field, f. Okay? And let f prime be a polynomial with coefficients in the second field. And let this polynomial be obtained by applying phi to the coefficients of f of x. So you take this polynomial f of x, which has coefficients in f, and then you apply the isomorphism that takes f to f prime. So all of the coefficients of f get sent to elements in f prime, and these become the coefficients of f prime. Right. So you have this polynomial, and it gets sent to this polynomial via this isomorphism of the ground fields. Right. So let E be a splitting field for the first polynomial over f, and let E prime be a splitting field for the second polynomial over f prime. Right. So the claim of this theorem, the point of this theorem, is that the isomorphism phi extends to an isomorphism sigma of the splitting fields. So basically what it's saying is, if you have it's basically saying that these splitting fields are unique, right? And that's actually that's going to be the corollary to theorem 27. It's going to say that the splitting field of a certain polynomial is basically unique up to isomorphism of fields, and we're proving it in this theorem, theorem 27. So yeah, you have two fields that are isomorphic. You have a polynomial in the first field, you have the splitting field of that polynomial. You look at the corresponding polynomial under the isomorphism in the second field and the splitting field of that polynomial, and then you're saying that these two splitting fields are the same, and in fact they're isomorphic via an isomorphism that extends the original isomorphism between the ground fields. Let me check if there are any messages. Right. So that's a statement of the theorem. It's basically telling you that splitting fields are unique, and let's try to prove this. Right. So again, we're given this isomorphism between the ground fields, f and f prime, and then we want to construct an isomorphism between the splitting fields, e and e prime. Right. So how are we going to do this? Let's do induction on the degree of the polynomial for which we're constructing the splitting field. So, okay, here's some facts first. We have an isomorphism between the ground fields, f and f prime. So this should be prime. So we have an isomorphism phi between the ground fields, and this induces a natural isomorphism between the polynomial rings. So the polynomials with coefficients in f and the polynomials with coefficients in f prime. You just send x to x, and you send the coefficients to these coefficients via this isomorphism. Right. So now the polynomial f of x and f prime of x correspond to each other via this isomorphism between the polynomial rings. And furthermore, the irreducible factors of f and the irreducible factors of f prime also correspond 1 to 1. So if you split this guy into its irreducible factors, each of those factors is going to correspond under this isomorphism to each of the factors of the corresponding polynomial f of x, f prime of x. Okay, so that's one fact. I think now we're going to use this to do the base case, which is so again, the proof strategy is to do induction, right, on the degree n of f, and right now we're doing the base case. Okay, so first let me just say something. So if f of x has all of its roots in f, then f of x splits completely in this polynomial ring fx. And via the isomorphism, we know that f prime of x also splits completely in the corresponding polynomial ring f prime of x. So since f of x splits completely in this field, the splitting field of this polynomial is just the ground field f, right? So e equals f, and furthermore, e prime equals f prime. The splitting field of the corresponding polynomial is also just the ground field of the corresponding field, right? So since we have already an isomorphism between f and f prime, we just take the isomorphism between the splitting fields to be the same as this, because they're all the same field. So now we know that we constructed the isomorphism between the splitting fields, because the splitting fields were just the ground fields, and we already have an isomorphism between them. So this proves the result for the base case, n equals 1. Why am I calling this the base case? Because this is the case where all of the irreducible factors of f have degree 1. So that's the point, right? So we're inducting on the degree, and all of the irreducible factors of f over f have degree 1. It splits completely, right? So that's the base case, right? Okay, now the hard part is the induction step. So the induction step, you have to assume the theorem to be proved for a field f, an isomorphism phi, and a polynomial f of x of degree less than n. Right. So assume by induction that the theorem holds for all things like this, right? Any field f, any isomorphism phi, and any polynomial f of x of degree less than n. So this is the induction hypothesis, and now we're gonna try to do some things, right? So let p of x be an irreducible factor of f of x with degree greater than or equal to 2. So in this base case, we already took care of all the cases where the irreducible factors have degree 1. So let's just change that. Let's say it has degree greater than or equal to 2. So this, together with this, is considering all of the cases, right? So let p of x be an irreducible factor of f of x with degree greater than or equal to 2. So this is an irreducible factor. And let p of x be p prime of x be the corresponding irreducible factor of f prime of x. So via the isomorphism, you get that corresponding irreducible factor. Okay, let alpha be a root of p of x, and let beta prime be a root of, should it be beta prime or just beta? I think it should be beta. Right, so let beta be a root of p prime of x. Okay, and then by theorem 8, so this was in an earlier section, it says if you have basically the concept of this theorem was that if you have an isomorphism between fields and you have a polynomial, irreducible polynomial here and corresponding irreducible polynomial here, and you extend the field by a root of this irreducible polynomial and also extend this field by a root of this irreducible polynomial, then there exists an isomorphism between those new fields, which extends this. So by theorem 8, we have the existence of sigma prime, which is an isomorphism between f adjoin alpha and f prime adjoin beta. So f adjoin a root of this irreducible factor and f prime adjoin a root of this irreducible factor. Right. So we have that isomorphism, and now to complete the proof we just use induction, because now so we have this isomorphism, and now we're going up to the whole splitting field, right? What is the so E is the splitting field over f of the polynomial f of x. Let me write this down. So E is a splitting field for over f of the polynomial f of x, right? But it's also the splitting field over it's also the splitting field over f adjoin alpha of, so if you just factor f of x in this field, it's going to be like x minus alpha times g of x, right? I think we didn't use g before. No, we didn't use g. So in this field, in the polynomial ring with coefficients in this field, you can factor out this linear factor x minus alpha because alpha is in that field, right? So you can factor that out, and now you have g of x remaining, and E is actually the splitting field of f adjoin alpha of the polynomial g of x, right? And furthermore, what do you notice about g of x? It has degree less than n, right? Yeah. And the point of the induction step was that we assumed we have the result for all polynomials of degree less than n, right? So yeah. So that's the point. So we go up to this extension, f adjoin alpha. We have the isomorphism there from a theorem we proved earlier, and then going from there to the full algebraic splitting field, we get the isomorphism via the induction step, right? Okay. Are there any questions about that argument? Was it clear enough? Okay, so someone says perhaps at the end we can look at the idea of the proof of theorem 8 again. Sure, I think we can do this. Where did we do this? So I think that was in section 13.1. Okay, so I think it was this theorem. Let's see. So you have an isomorphism f between two fields. So it's an isomorphism of fields. We have a polynomial p of x with coefficients in f, which is irreducible, and the polynomial p prime of x with coefficients in f prime, which is obtained by applying phi to the coefficients of p of x. So it's the same situation, but these are irreducible. And alpha is a root of p of x, and beta is a root of p prime of x. And the conclusion of this theorem is that f adjoin alpha is isomorphic to f adjoin beta via an isomorphism extending phi, taking alpha to beta. And the proof, so, the proof probably is like, so I wrote it in this one line. So it's like f adjoint alpha is isomorphic to the polynomial ring with coefficients in f mod the maximal ideal generated by p, which is isomorphic to, so first of all, this isomorphism is another theorem, and it's very important to understand this isomorphism. I did it on Wednesday. Yeah, so this is it. This is whenever you have an irreducible polynomial, adjoining a root to the ground field is the same thing as modding the polynomial ring by that irreducible polynomial. So this root is like the role of x, where it satisfies this polynomial relation, p of x. And then to construct this isomorphism, you probably take the isomorphism from f to f prime, right, given by phi, and send x to x. And then notice that this would send this maximal ideal to this maximal ideal. So then you get an isomorphism of fields by, like, I guess, first isomorphism theorem. Right, and then you use the same theorem that you use for the first isomorphism for the second isomorphism. So that so really the key is like understanding this and then using, I guess, first isomorphism theorem to get this. Okay, so that's basically the idea. Any questions about that? Okay. Cool. Now let's go back here. Where are we? So, all right. So where are we now? So, corollary 28 is the uniqueness of splitting fields, which says that any two splitting fields for a polynomial f of x with coefficients in f over f are isomorphic. So this is what I promised the last theorem was about. So what you do, you specialize the last theorem with the isomorphism being the identity between f and f, right? So now f and f prime are the same, and this is just the identity isomorphism. And so you take E to be a splitting field of a polynomial f, and you take E prime to be the splitting field of the same polynomial f, like the identity takes f to f, right? And you say they're two distinct splitting fields. Okay, sure. But then the previous theorem told you that you get an isomorphism extending this identity map, right? So that says that these splitting fields are actually the same. You just have the same splitting field via it's same up to isomorphism. Okay, so this justifies the notion of saying the splitting field for a polynomial f, because they're unique up to isomorphism. So you can say, let's consider the splitting field of this polynomial. All right. Let me see any questions. All right. Now let's start talking about algebraic closures. So this is the main point, right? So the of today is algebraic closures. So let's start talking about that. All right. So a definition, the field f bar is called an algebraic closure of f if f bar is algebraic over f and every polynomial f of x with coefficients in f splits completely over f bar. So what is this saying? So this extension f bar, so it's some extension of the base field f. It's called an algebraic closure if, first of all, it's algebraic, and second of all, any polynomial with coefficients in f splits completely over this new field f bar. So basically, give me any polynomial with coefficients in the ground ring, I can find all of its roots in this algebraic closure. So that's what algebraic closure means. Second definition, a field K is said to be algebraically closed if every polynomial with coefficients in K has a root in K. So Um, okay, so what is this definition saying? So a field K is algebraically closed if every polynomial with coefficients in K has a root in K. So give me any polynomial with coefficients. So here, the point is algebraically closed is a property of a field itself, and algebraic closure is an extension of a field. So you take a field and then you can extend it to get some algebraic closure, but algebraically closed means you take a field and then ask, is it algebraically closed, right? So this field itself is algebraically closed if you take any polynomial with coefficients in this field and it has a root in this field, right? And algebraic closure means you take any polynomial with coefficients in a ground field and it has roots in the extension. It splits completely into extension. All
Okay,
right.
so is F bar non-unique then? Is that correct?
Oh, so that's a good point, right? So is F bar we don't know yet, right? We don't know if this is unique, but it turns out that it is unique. I think we'll see that later down in the
Okay,
notes. Yeah.
I'm just imagining like you have an algebraic extension of F bar itself, and it would seem that the algebraic extension of F bar is also an algebraic closure over F by this definition.
No.
Uh,
No.
no.
So okay, let me give an example. I'll put the example here. Right. So okay, let's say you have Q. Am I highlight? Yes. Okay, so let's say I have Q, right? And then an algebraic extension is like Q adjoin square root of 2, right? Um okay, so this is an algebraic extension.
Yeah.
This is an algebraic extension, but it's not. This algebraic extension is not an algebraic closure because there are polynomials with coefficients here which don't have roots, which don't have all
Yeah.
of their roots here. Right?
Yeah. So I'm imagining an algebraic extension of F bar itself, right? So like if
Oh, I see.
um
Yeah,
in
I see what
in
you mean.
that
Yeah, yes,
yeah.
that's correct. So if you have F, and then you have something called its algebraic closure, and then you have an extension of this, say, um, I don't know what letter.
It's like it's a K or whatever.
Yeah, K, right? And say this is algebraic. Then the whole extension is also algebraic, and it's necessarily also an algebraic closure. Right.
Okay. And so in that sense, algebraic closures are not unique,
Yeah.
possibly,
Yeah.
but you want like the minimal element somehow of this chain or something. Like,
Yeah.
okay.
Yeah. Okay.
All right.
All right.
Thank you.
All right. So let's continue. So it's not obvious that algebraically closed fields exist, and it's nor okay. So this says nor that there exists an algebraic closure of a given field. Right. Okay. So it's not obvious that they exist, nor that there exists algebraic closures of a given field. So a second note, if K is algebraically closed, then in fact every polynomial f of x has all of its roots in K, right? So the definition of algebraically closed meant that every polynomial with coefficients in K has a root, but this forces it to have all of its roots in K. Why? So K is algebraically closed. Wait. Okay, so I need to say something about this. Right, so say K is algebraically closed. And you have some polynomial p of x, right? And it has a root in K. So then you can factor it like x minus alpha times g of x, right? And then g of x has a root in k, so you can factor that as x minus alpha times x minus beta times h of x. And you can keep on doing this until you get all of the roots of p of x and it splits completely. So that's how you know that if it's algebraically closed, then it has all of its roots. Okay. I don't know why. Okay. Yeah. So in conclusion, if k so k algebraically closed means that k is its own algebraic closure. Right. Algebraic closure means every polynomial splits completely, and we just showed that every polynomial does split completely. So we write that as k equals k bar. And the converse is also obvious. So like if you have k equals k bar, then that means it's algebraically closed, because what that k equals k bar means so any polynomial with coefficients in k has all of its roots in k, and that means it has some root in k. So that's how the backwards implication is obvious. Right. If it has all of its roots, then it actually has some root. Right. So k is algebraically closed if and only if k equals k bar. And going back to this situation, so f is an algebraic closure of f bar is an algebraic closure of f. So okay, hold on. Let me do this proposition. So this proposition says f double bar is equal to f bar. So the algebraic closure of the algebraic closure is yeah. Yeah. So
Yeah. So just,
yeah.
well, it's just like part of what I was getting at in the other question was that it feels kind of weird to give a specific notation to something that isn't like this bar notation. Like it's not a function that takes in a field and gives out a field. Like it just denotes that f bar is an algebraic closure of f, right? And so is this claim saying that like the bar is an operation that gives another field, or is this claim saying that an algebraic closure of an algebraic closure is an algebraic closure?
Yeah, it's just saying that that's what it's saying. It's saying an algebraic closure of an algebraic closure is an algebraic closure.
Okay, so it's not like an operation on fields. It's just
no. So okay, so what this is actually saying is right. So this f bar is a algebraic closure of f. So is k. K is a algebraic closure of f. But what it's saying is f bar is also a algebraic closure of itself. Okay, so that's the content of this theorem. So what it's saying is let f bar be an algebraic closure of f, then f bar is algebraically closed. Okay, so how are we going to prove that it's algebraically closed? Let f of x be a polynomial in the polynomial ring with coefficients in f bar. We want to show that it has a root in f bar. So let alpha be a root, and we want to show that alpha is also in f bar. So the way we do this, we take the algebraic extension f bar adjoint alpha. So this is above f bar, right? And it's an algebraic extension. So because we're adjoining an algebraic element. But then f bar is also algebraic over f, right? By definition. So the composite, no, the full extension f bar adjoint alpha is also algebraic over f. So that means alpha is algebraic over f. Yeah. So going from this step to this step, we took alpha to be a root of a polynomial with coefficients in f bar, and now we concluded that alpha is a root of a polynomial with coefficients in f. Right. So it's kind of subtle. You took it to be a root of a polynomial with coefficients in f bar, and now you conclude it's a root of a polynomial with coefficients in f. And so actually alpha is an f bar, because every polynomial with coefficients in f has all of their roots in f bar. So f bar is algebraically closed. Okay. All right. Now, so this is almost basically the last thing in this section, is how to construct algebraic closure of a given field. So I said before, it's not obvious that you do have algebraic closures of any given field, that there exists an algebraic closure of that field. And so we're going to try to prove this here. Let me check for questions. Okay. Alright, so proposition 30 says for a field f, there exists algebraically closed field K containing f. Okay, so I didn't write down the proof, and it doesn't even look like we have time to show this, but yeah, I'm just going to skip this for now. So it says a field f, there exists an algebraically closed field K containing f. So a field that any polynomial in f has all of its roots in K. We saw that the use... okay, now we're going to use this proposition to construct algebraic closure of f. Okay, algebraically closed field containing f, construct an algebraic closure of f. Alright, so proposition 31, let K be an algebraically closed field and f be a subfield of K. The collection of elements f bar of K that are algebraic over f is an algebraic closure of f. And an algebraic closure is unique up to isomorphism. So what we're saying is this subfield of elements, that the subfield consisting of algebraic elements over f is unique up to isomorphism. Okay, so by definition, f bar is an algebraic extension of f. Every polynomial with coefficients in f splits completely over K into linear factors x minus alpha. So we're using the fact that K is algebraically closed. Yeah, so the fact that K is algebraically closed means any polynomial with coefficients in f splits completely over K, right? So any polynomial with coefficients f splits completely in K. So now what we want to show that each alpha is actually an element of f bar. So alpha is a root of f of x, so alpha is algebraic over f, and hence an element of f bar. So all of these roots are actually, we knew they were in K, but they're actually in f bar, which is the collection of algebraic elements, algebraic over K elements. Algebraic elements, wait, they're the collection of algebraic over f elements in K. Right. So f of x splits completely in this polynomial ring, and so f bar is an algebraic closure of f. And then the uniqueness of this up to isomorphism, it's omitted even in the textbook, but they say it appeals to uniqueness of splitting fields, and an application of Zorn's lemma. Alright, so the next thing is the fundamental theorem of algebra, which says that the field C is algebraically closed. So any polynomial with coefficients in C splits completely in C, has all of its roots in C. And the proof of this, you can give proofs using analysis. You can also prove it using Galois theory, which we'll get to later on. And a corollary of this is that the field C contains an algebraic closure for all of its subfields. In particular, Q bar, the collection of complex numbers algebraic over Q, is an algebraic closure of Q. So in this notation, Q bar is the subfield of elements of C which are algebraic over Q. Yeah. And the point of all this is that all computations involving elements algebraic over F may be viewed as taking place in one large field, namely F bar. In the case of Q, for finite extensions of Q, we may consider all our computations as occurring in C. So the point of all this algebraic closure business is that whenever you're dealing with finite extensions of Q, you can view them as embedded in C or embedded in Q bar. And so you can take the composite field of these finite extensions and they'll still be inside of C. So it makes everything a bit nicer, right? Easier to work with because everything is happening in the same place, right? All right. So that's the end of this section, and yeah, I omitted the proof of 30, which is really like where all the hard work is, right? For any field F, there exists algebraic closed field K containing F, but that's in the book, and this is all I have time for today, right? Are there any questions? Right, so that's it for today. If you have any questions, just ask. But the next lecture is on Monday. Can you give a really quick and rough outline of why C is algebraically closed? I'd actually have to look at this in detail. I don't remember it off the top of my head. Yeah, the book didn't give a proof, but we will see a proof later on using Galois theory, and there are other proofs, but I'd have to look them up. I don't know one off the top of my head.